All right, let's go.
Number 10. What the Planck scale actually is. The wall at the end of physics. Before any theory, before any speculation, a number. 1.616 times 10 to the minus 35 meters. That is the Planck length, the smallest meaningful length that current physics can describe. Not the smallest thing that exists, the smallest thing our equations can say anything coherent about. Below this scale, the mathematics of both quantum mechanics and general relativity simultaneously break down. Not one of them, both of them at the same time. To understand how small this is, a proton is roughly 10 to the minus 15 meters across. The Planck length is 10 to the minus 35. The Planck length is to a proton what a proton is to the observable universe. 20 orders of magnitude smaller than the smallest thing we can currently probe with the most powerful particle accelerator ever built. The Large Hadron Collider probes scales of around 10 to the minus 19 meters. The Planck scale is 10 to the minus 35. The gap between what we can currently access experimentally and the Planck scale is 16 orders of magnitude. Closing that gap with current technology would require a particle accelerator the size of the Milky Way galaxy. We are not getting there experimentally anytime soon, but we have mathematics, and the mathematics points to this scale as the place where everything we know about physics stops working, where space and time as we understand them may cease to have meaning, or something fundamentally different from anything in our current theories must be happening. Every theory on this list is an attempt to describe what that something is. Number 9. Quantum foam. Space-time that boils. John Wheeler, one of the physicists who coined the term black hole, proposed in 1955 that at the Planck scale, space-time is not smooth. It is not a calm, flat fabric that matter and energy move through. It is a seething, violent foam. Quantum mechanics demands it. The Heisenberg uncertainty principle, which says you cannot simultaneously know the exact position and energy of any system, applies to space-time itself. At the Planck scale, the uncertainty in energy is so large and the scale so small that quantum fluctuations create violent distortions in the geometry of space-time. Tiny wormholes appear and disappear. Topology changes. The smooth, continuous space-time of general relativity becomes a chaotic, bubbling foam of geometry, constantly changing, constantly fluctuating, constantly violating the smooth picture that works perfectly at human scales. Wheeler called it quantum foam, also called space-time foam. The smooth space-time we experience, the one that general relativity describes so precisely, is an average, a statistical smoothing out of the underlying quantum chaos, like a calm ocean surface that is actually made of billions of individual chaotic water molecules. Quantum foam has profound implications. If space-time is foamy at the Planck scale, then very high-energy photons traveling across cosmic distances should interact with the foam, acquiring a slight fuzziness in their arrival times depending on their energy. Higher-energy photons should arrive very slightly later than lower-energy ones from the same source because they interact with the foam more strongly. Gamma ray bursts, intense bursts of high-energy radiation from across the observable universe, are perfect test sources. Instruments, including the Fermi Gamma Ray Space Telescope, have looked for exactly this energy-dependent time delay. No delay has been found. The arrival times of photons from gamma ray bursts show no energy dependence at the level quantum foam models predict. This either rules out the simplest versions of quantum foam or suggests the foam is more structured than Wheeler's original proposal. The debate is ongoing. The experimental constraint is real. Quantum foam in its original form is under pressure. But the underlying idea that spacetime at the Planck scale is not smooth remains one of the most deeply motivated proposals in theoretical physics. Something must happen when quantum mechanics and gravity collide. Wheeler's foam is the most intuitive picture of what that something looks like. Number 8. Loop quantum gravity. Space is made of atoms. General relativity treats space as continuous, Infinitely divisible. You can always zoom in further and find more space between any 2 points. There is no smallest unit of space. Loop quantum gravity says this is wrong. Developed primarily by Lee Smolin, Carlo Rovelli, and Abhay Ashtekar through the 1980s and 1990s, loop quantum gravity is one of the 2 leading candidates for a theory of quantum gravity, a theory that reconciles quantum mechanics with general relativity. Its central claim is radical. Space is not continuous. Space is made of discrete, indivisible units, quanta of space, just as energy is made of discrete quanta in quantum mechanics. The smallest possible chunk of space has an area of roughly 1 Planck length squared. You cannot have a region of space smaller than this. There is no more space between 2 adjacent quanta of space. They are adjacent, no gap. These quanta of space are not particles sitting in space. They are space. The network of connections between these quanta, described mathematically by structures called spin networks, is what space is. Geometry is not a backdrop for physics. Geometry is the physics. The spin network is the universe at the Planck scale. Time in loop quantum gravity is equally discrete. It does not flow continuously. It advances in discrete Planck time steps, each step approximately 5.4 times 10 to the minus 44 seconds, the smallest possible tick of any clock. Between Planck time steps, nothing happens, not because things are frozen, but because the concept of between doesn't exist. Time is not continuous, it is granular. The implications for the Big Bang singularity are significant. In standard general relativity, the Big Bang is a singularity, a point of infinite density where the equations break down. In loop quantum gravity, the discrete nature of space prevents infinite density. As the universe is compressed toward the Planck density, quantum effects generate a repulsive force, a quantum bounce that prevents singularity formation. The Big Bang was not a beginning from nothing, it was a bounce from a previous contracting phase. Loop quantum gravity has not yet made a confirmed experimental prediction. It is a mathematically consistent framework for quantum gravity that has not yet been tested, but it is one of the most developed alternatives to string theory, and it makes specific predictions about the cosmic microwave background and the spectrum of primordial gravitational waves that future observations may test. Number 7. String theory at the Planck scale. Everything is vibration. String theory proposes that the fundamental constituents of reality are not point particles, electrons, quarks, or photons, but one-dimensional vibrating strings of energy. Different modes of vibration of the same fundamental string correspond to different particles. An electron is a string vibrating one way, a quark is the same string vibrating differently. A graviton, the hypothetical particle that carries gravity, is a string vibrating in a specific mode that automatically emerges from the mathematics. At human scales, and even at the scales probed by the Large Hadron Collider, particles look like points. The string nature only becomes apparent at the Planck scale, where the length of the strings becomes relevant. Below the Planck scale, in string theory, the concept of distance itself breaks down. There is a minimum distance, approximately the string length near the Planck scale, below which you cannot probe. Trying to concentrate energy into a smaller region just creates a larger string rather than revealing smaller structure. This is called T-duality. In string theory, a universe compactified to a radius of r is physically equivalent to a universe compactified to 1 over r in Planck units. Probing very small distances is equivalent to probing very large distances. The distinction between large and small breaks down at the Planck scale. Space below the string length is not smaller space, it is the same space from a different perspective. String theory also requires extra dimensions, 6 or 7 additional spatial dimensions beyond the 3 we experience, compactified at the Planck scale. These extra dimensions are not accessible at energies we can currently produce. They are curled up too small to detect, but they are fundamental to the consistency of the theory. The landscape problem haunts string theory at this scale. The compactification of extra dimensions can be done in approximately 10 to the power of 500 different ways, each producing a different universe with different physical constants. String theory does not predict our specific universe. It predicts a vast landscape of possible universes, of which ours is one. Why we inhabit this particular vacuum rather than any other is not answered by the mathematics. String theory has produced extraordinary mathematics and has deeply influenced theoretical physics for 4 decades. It has not produced a confirmed experimental prediction. As of May 2026, it remains the most developed framework for physics at the Planck scale, and the most debated. Number 6. The Holographic Principle. The Planck scale as a pixel size. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something extraordinary about black holes. The entropy of a black hole, a measure of its information, is proportional not to its volume but to its surface area, specifically to its surface area measured in units of Planck length squared. 1 Planck area, 1 bit of information. The entire information content of a black hole encoded on its 2-dimensional surface at Planck scale resolution. Gerard 't Hooft and Leonard Susskind developed this into the holographic principle. The information content of any region of space is bounded by its surface area in Planck units, not its volume. 3-dimensional reality may be a projection from 2-dimensional information encoded at the Planck scale on the boundary of space. The Planck length in this framework is not just the scale where physics breaks down. It is the pixel size of reality, the fundamental resolution of the universe. Below the Planck length, there is no more information, not because space isn't there, but because the holographic encoding has no finer grain. The ADS-CFT correspondence, a precise mathematical duality between a theory of gravity in a higher dimensional space and a quantum field theory on its boundary, provides the most concrete realization of the holographic principle. It is one of the most studied results in theoretical physics of the past 30 years. It has been used to calculate properties of quark-gluon plasma produced in heavy ion collisions at the relativistic high-ion collider, with results matching experiment. The holographic principle is not speculation. It is a framework with real computational power that produces results matching observations in specific physical systems. Whether it reflects the fundamental structure of reality at the Planck scale, whether the universe is literally a hologram, remains one of the deepest open questions in physics. Number 5. Causal dynamical triangulation. Building spacetime from triangles. How do you do quantum gravity without assuming spacetime is smooth? One approach is to build spacetime up from the smallest possible pieces and see what emerges at larger scales. Causal dynamical triangulation, developed by Jan Amjorn, Renate Lal, and Jerzy Yurkovits starting in the late 1990s, does exactly this. It models spacetime as built from tiny 4-dimensional simplices, the 4-dimensional equivalent of triangles. Each simplex has a size at the Planck scale. Spacetime is assembled from these building blocks by summing over all possible ways they can be connected, a quantum mechanical sum over all possible spacetime geometries. The causal part is crucial. The triangulation respects causality. Each simplex has a well-defined past and future. Earlier attempts without this constraint produced spacetime that looked nothing like the universe we observe, fractal structures that crumpled into either 2-dimensional sheets or branched polymers depending on the coupling constants. With causality imposed, something remarkable happens. The sum over geometries spontaneously produces a spacetime that, at large scales, looks like the 4-dimensional de Sitter space, the geometry of an expanding universe that general relativity predicts and that observations confirm. Nobody put de Sitter space in. It emerged from Planck-scale building blocks obeying causality. The approach also finds that at very small scales, spacetime becomes effectively 2-dimensional. The fractal dimension of spacetime decreases from 4 at large scales to approximately 2 at the Planck scale. This dimensional reduction at small scales also appears in loop quantum gravity and in certain approaches to string theory, suggesting it may be a genuine feature of quantum spacetime rather than an artifact of any specific approach. A universe built from Planck-sized triangles that spontaneously grows into the large-scale geometry we observe. It is not the whole story, but it is a remarkable result from a simple starting point. Number 4. The Firewall Paradox, the crisis at the Planck scale. In 2012, 4 physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully published a paper that created a crisis in theoretical physics. It became known as the Amps paradox or the Firewall Paradox. The argument goes like this. Quantum mechanics demands that information is never destroyed. If you throw a book into a black hole, the information it contains must eventually escape, encoded in the Hawking radiation the black hole emits as it evaporates. General relativity demands that an observer falling into a large black hole should notice nothing special at the event horizon. The event horizon is not a physical surface, it is just a mathematical boundary. An infalling observer should cross it smoothly and not experience anything dramatic. These two demands, information preservation and smooth horizon crossing, appear to be mutually exclusive. If information escapes in Hawking radiation, the quantum state of the radiation must be entangled with the interior of the black hole. But quantum mechanics forbids a quantum state from being maximally entangled with two different systems simultaneously. If the outgoing radiation is entangled with earlier radiation to preserve information, it cannot also be entangled with the interior. The entanglement that normally makes the horizon smooth is broken. What replaces it is a wall of high-energy radiation at the horizon, a firewall that would incinerate any infalling observer. The firewall paradox forces a choice. Either information is destroyed, violating quantum mechanics, or the horizon is not smooth, violating general relativity, or something happens at the Planck scale that resolves the paradox in a way that none of our current theories can describe. The ER equals EPR proposal by Juan Maldacena and Leonard Susskind in 2013 suggests that entangled particles are connected by microscopic wormholes. The entanglement between outgoing Hawking radiation and the black hole interior is geometrically realized as a wormhole connecting them. The firewall is avoided because the geometry itself resolves the apparent contradiction. Whether this resolution works and what it implies for Planck-scale physics is one of the most actively debated questions in theoretical physics as of May 2026. The firewall paradox has not been resolved, it has been sharpened. Every proposed solution reveals deeper questions about what happens at the interface of quantum mechanics and gravity. Number 3. Doubly special relativity. A speed limit and a length limit. Einstein's special relativity introduced a universal speed limit, the speed of light, the same in every reference frame for every observer, regardless of their motion, a fundamental constant of nature. Giovanni Amelino Camellia proposed in 2001 that the Planck length might be a second universal constant of the same type, not just a length that appears in equations, but a fundamental minimum length that is the same for every observer in every reference frame, invariant under all transformations, just as the speed of light is invariant. This is doubly special relativity, two fundamental constants, the speed of light and the Planck length. The implications are significant. If the Planck length is truly invariant, if every observer, regardless of their motion, measures the same minimum length, then the standard rules of special relativity must be modified at high energies approaching the Planck scale. The energy, momentum, and velocity relationship gets corrections. The dispersion relation, the equation relating a particle's energy to its momentum, gets modified at Planck scale energies. These modifications are tiny at ordinary energies, completely undetectable, but at very high energies approaching the Planck energy of approximately 10 to the 19 billion electron volts, they become significant. The observable signature is the same as for quantum foam. High-energy photons from gamma-ray bursts should travel at slightly different speeds than low-energy photons if doubly special relativity is correct. The Fermi Gamma-Ray Space Telescope has constrained these modifications severely, ruling out the simplest linear corrections. But doubly special relativity allows for different forms of the modification. Some versions remain consistent with current observations. The framework is alive and makes predictions that next-generation gamma-ray observatories will test further. A universe with two fundamental invariants rather than one, a speed limit and a length limit, both written into the structure of spacetime. Number 2. The information paradox and Planck scale remnants. What if black holes leave something behind? When a black hole evaporates through Hawking radiation, losing mass continuously until it reaches zero, what happens at the end? Standard calculations say the black hole simply disappears, complete evaporation, nothing left. But this creates the information paradox. All of the information about everything that ever fell into the black hole appears to be gone. Quantum mechanics says information cannot be destroyed. Something is wrong. One proposed resolution is Planck scale remnants. As a black hole evaporates, it gets smaller and hotter. The temperature of Hawking radiation increases as the black hole shrinks. When the black hole reaches the Planck mass, approximately 21 micrograms, the temperature reaches the Planck temperature, and the standard Hawking calculation breaks down. Quantum gravity effects dominate. We do not know what happens next. One possibility is that the evaporation simply stops at the Planck scale. A stable Planck mass remnant is left behind, a tiny object of Planck size containing all of the information about everything that ever fell into the black hole. The information is not destroyed, it is locked into the remnant. The problems with this proposal are significant. A Planck mass remnant containing the information of a stellar mass black hole, which could have consumed stars and planets containing vast amounts of information, would need to have essentially infinite internal states, an object of Planck size with infinite internal complexity. This violates expectations from statistical mechanics and creates other theoretical problems. But the alternative that the information is truly gone violates quantum mechanics, and the alternative that information escapes in Hawking radiation requires a mechanism at the Planck scale that nobody has fully specified. Planck scale remnants are not the favored solution, but they have not been ruled out, and every other proposed solution has its own serious problems. The end state of black hole evaporation remains genuinely unknown. It is one of the places where ignorance about Planck-scale physics has direct observable consequences, in principle. In practice, the smallest black holes we know about would take times vastly longer than the current age of the universe to evaporate to the Planck scale. We cannot observe it directly. But the question does not go away just because we cannot observe the answer. Number 1. We are at the edge, the most honest position in physics. Here is the truth that sits underneath every theory on this list. Nobody knows what happens at the Planck scale. Not approximately, not almost. Genuinely, completely do not know. Every theory discussed here is a serious proposal made by serious physicists using serious mathematics. Every one of them is internally consistent. Every one of them has features that seem right. Every one of them has features that seem wrong or incomplete. Not one of them has been confirmed by experiment. Not one of them has produced a prediction that was tested and verified at energies anywhere near the Planck scale. The Planck scale is not just experimentally inaccessible. It is the scale where our two best theories of reality, quantum mechanics and general relativity, both are simultaneously valid and simultaneously incompatible. Quantum mechanics works perfectly at small scales. General relativity works perfectly at large scales and with strong gravity. At the Planck scale, both apply and their predictions conflict. A theory of quantum gravity, a theory that reconciles them, is the single most important unsolved problem in fundamental physics. It has been the single most important unsolved problem in fundamental physics for nearly a century. Every approach described on this list is a candidate for that theory. None of them is the confirmed answer. What we do know is that something happens at the Planck scale, something that our current theories cannot describe, something that may rewrite our understanding of what space is, what time is, what information is, and what reality is made of at its most fundamental level. The Planck scale is the wall at the end of physics, and somewhere on the other side of that wall is the deepest truth about the universe that physics will ever reach. We are standing at the wall. We can hear something on the other side. We just cannot see through it yet. 10 theories about what happens at the Planck scale, from space-time that foams and boils to space made of discrete atoms, from strings vibrating at the smallest possible scale to pixels of information on a holographic boundary, from triangles assembling into a universe to firewalls burning at the edge of black holes, from a second universal constant written into nature to remnants preserving information at the end of everything. The Planck scale is where physics runs out of road, and the next theory, the one that finally sees past the wall, will be the most important scientific discovery in human history. Subscribe to Cosmic Hives. See you in the next one.